All right. The time is 3 o'clock. Welcome everybody to RISE Learning Machines seminars. RISE is Sweden's public research institute with nearly 3,000 people working on a wide array of topics. Specifically, the computer science department works on applied AI projects for the benefit of society, and we organize these seminars every week. Today, I have the pleasure to introduce Adam Breitholtz, who is a PhD candidate at Chalmers University of Technology and who works on problems in domain adaptation. I will remind everybody that this meeting will be recorded, and if anybody wants to be removed from this recording, just let us know. You can, for example, drop me an email afterwards. So Adam is also supervised by Fredrik Johansson at Chalmers, and he's been working as a PhD candidate since 2020. The topic today will be domain adaptation and with the use of privileged information.
So, hello everyone. My name is Adam. As also nicely introduced. And here I'm going to talk about our work, provable domain adaptation using privileged information. And this is joint work with my dear colleague Anton and our supervisor, Fredrik Johansson. So in this work, the principal problem that we're trying to solve is that of unsupervised domain adaptation. And in UDA, we want to learn a mapping predicting target labels Y from the input features X. And the general setup is that we have two source domains, which is distributions over the product space of input features and labels, where we have the source domain, where we have most information from. We have both input features and labels, and the target domain, where we only have the input features available during training. And from this, we would like to construct such a mapping that we can predict Y from X. However, in the most general case, where we allow the source and target domain to differ arbitrarily, this is a problem that in general is not solvable. So we have to make assumptions to sort of simplify down and constrain the problem to be able to say something. The most common sets of these assumptions, we argue, are fairly unrealistic. That is to say that they are violated in practical applications. So what are these assumptions then? This is a common set of assumptions in UDA, covariate shift and overlap. Covariate shift being that the underlying or the true function that we're trying to estimate are the same in both domains, and overlap or overlapping support, which just means that if we have some probability of observing a data point in the target domain, that means that we also have the probability of observing it in the source. So essentially, we're just saying that it's nothing new here. We've had some possibility of seeing this before. And this second one is what's causing the headache, so to speak. This is what we believe can be violated in an actual application. So to illustrate, I have made this little image here where we have the source in the black ellipses and the dashed ones are the target. A here being the regular supervised learning case where the source and target domains are the same, or the distributions. B here is where we lack overlap. Of course, we have a little part of the ellipsoids which overlap, while we have this extra part which does not really have any data points from the source in it, so we have no information what to predict over there. So in this case, it would be a difficulty, but of course we can have the overlapping case where this is fulfilled. But we argue that this is not always probable. So as an example, I've made these two images. So let us say that, for example, we have a source domain, all these boat images, very low resolution, of course, but we have also this superimposed digit over them. We would like to predict which digit it is. As a target, we have these frogs or animals instead, with these same digits imposed over them. The issue is here that the backgrounds here are quite distinct and different. And it is not entirely clear, or rather also it's unlikely that it would overlap would hold here, because there's a lot of sort of extraneous information that might not actually be present in the target set because of the differing backgrounds. However, if we could somehow constrain ourselves to the parts around these digits somehow, perhaps, then it would be much more likely that overlap would hold, because the digits look the same. The only difference then would be that we're cutting out most of the spurious information from the data. So in a sense here, we're saying that the location of the digit in the image somehow included would help with identifying it further. So how would we use such information? So the proposal that we have is that we assume that there is some information like this called W, which is overlapping in the domains that we consider, while still retaining some predictiveness of the label Y. This is similar to the idea of representation learning. That's very popular in UDA, but in representation learning, we try to learn representation which retains all these things, and we assume that we can find a representation that for which overlap and covariate still holds. But this is, of course, not something that we can verify. But the question we pose is that what if we have sort of supervision on this information instead? And what this will allow us to do is that will allow us to shift our assumptions a little bit to be with respect to this new information, W instead. So this is a type of learning called learning using privileged information. This is not something that we came up with. This is from Vapnik and Bashist. It's about 2009, if I don't misremember. And in this setting, we have, as in regular supervised learning, just our X's and Y's, but also this privileged information, W, as I've denoted here by this box over the X-ray image here. So this could really be anything from the original paper, but the privileged information helps in such a way that it speeds up the learning, is what is shown in the original paper. But you only have access to this information during the training, while at test time, you still only have the input features themselves from the target or the test here, and nothing else. So you can't explicitly depend on the privileged information in your classifier or hypothesis. So, sort of putting these two things together, we have a combination of learning using privileged information and UDA, which we call DALUPI, where we have, as in regular UDA, both input samples from the source and target domains, the source label associated to the source samples, but in addition, we also have these privileged information available for both source and target. While at test time, we still retain the same setting as UDA. We only have access to input features at test time. So we have some different examples here, where similar to what we had on the last slide, we have X-ray images and bounding boxes around regions of interest. And from that, we would like to make some classification of the pathology present. We have speech recognition, where we have some sort of tagging or speech tokenization as privileged information. And from that, we would like to produce a transcript. And then finally, we have a disease prediction. And disease prediction, I think, exemplifies well why this could be a reasonable setting, because we're actually asking for more information here. So one might very well ask, well, why don't you just go collect some labels from the target set if you're already collecting these other things, right? But if your disease prediction is that you want to predict maybe the outbreak of disease some time steps away from now, then that label is not available. It's going to happen in the future. But you can still have some additional sort of adjacent information like medical reports that are actually available at that time, and therefore this setting is reasonable in that sense. So to see the new assumptions that we can get in this setting is that we change the assumptions to be covariate shift and overlap with respect to the privileged information, W, instead. And in addition to these, we need to add another assumption to be able to ensure consistent learning. And this is the third sufficiency of privileged information. So what this essentially means is simply, as I said before, is W is sufficient to predict the outcome Y. So we'll be able to do sort of a two-step way, as we will see shortly. So, and this will need to be held in both the source and the target domains. But given that we have all these three, we can now ensure that we have consistent learning in this setting. So here's an illustration of the intuition that we have with why overlap with this W in mind might be better. So if we remember the example I had before, with this might not be very overlapping, but if we have some way to extract the privileged information, maybe a bounding box, or maybe the context within that, contents within that bounding box, and extract those, then we can suddenly see that it's much more probable that these would actually overlap, as I talked about before. So this is the overall idea that we have here. So based on this setting, we can now propose a very simple two-step algorithm. So we can go from input features, map that to privileged information space, and then go from there onto the labels using two mappings or functions, F and G, which we can learn from target and source data respectively. Then, of course, we can just compose these two mappings to form our final classifier H, which can simply predict Y from X, which was our goal all along. And under the assumptions, we can actually identify the optimal target hypothesis using this two-step methodology, is what we show in our work. So to quickly look a bit at the identification proof, we know that we can write the target risk in this way, just the expectation of losses and the target, and we just marginalize over W. We can use these assumptions together to get to this last line, where we see that we have only quantities which we can already estimate from what we've observed. So with T of X, which we have X's from T, we have W given X, we have both X's and W, so we can find this mapping. Same with the source, labels, and privileged information. So this all means that identification is indeed possible. We also show a simple generalization bound under our assumptions, again, where we have this composed function H of F and G. We can see here that, as one might expect, the target risk is then bounded by a weighted version of the source risk of G plus a regular risk, target risk of the F multiplied by some M, which is the Lipschitz constant. And we also have some sample generalization terms. The D and D prime and M and N are observations from source and target, and the pseudo dimensions of the respective classifier what am I saying? The space of classifiers we're considering for each of these mappings. One slight issue we might observe is that we have a 2 in the left-hand side, which would mean that this bound is probably not going to be very tight. However, it is still a generalization bound, so we can bound something in the setting, which is nice. The other results that we show in the paper, but I'm not going to talk about here, is that we have a quick proof sketch of a pack Bayesian style bound in the same form as I just showed, and also a bound on the target risk without the need for sufficiency of PI to be valid. So to go over to our experiments, we consider the use of this setting for image classification. Especially, we compare to regular supervised learning models, so source-only models, and the more Oracle style of have only seen targets models. As UDA baselines, we use a domain adversarial neural network and a network based on the margin disparity discrepancy to compare with. And we have the, I did rid of this, but maybe I can't. Oh well. We see at least that we have the different settings and what is observed in each setting here. Yeah. sorry. So yeah, this is what we're going to attempt to do. So first we're going to use this, as I showed you earlier, as the first synthetic experiment to test our two-step model. And in this we have images from CFAR that I've superimposed digits from MNIST into. And I've colored the digits with the mean color of the CFAR dataset. The source and target domains are the first 5 and second, or the last 5 classes from CFAR. So there's no shared backgrounds as such. And we give as information then the bounding box around the digits, as exemplified earlier. Formally, the privileged information here is actually the pixels within the box. But we can just put a deterministic function that extracts the pixels from any bounding box that we do pass in, and the theory should still hold. And to make this a bit more interesting, and to sort of see what happens when we add spurious correlations to this, we introduce this parameter epsilon that just denotes how likely it is for a certain background B to be correlated with a certain label Y. So it means that as epsilon grows larger and becomes closer to 1, maybe a 4 is actually always in the presence of a frog background instead of maybe a horse, and so on. Well, if epsilon is more closer to 1 over the number of classes, then it's just uniformly distributed over all the backgrounds. So we do this skew for different values of epsilon for the source domain data, and then we apply to the target domain data in testing. So the results are as follows. We can see that the orange line here is the source only model, which performs fairly well at first, but when the skew gets more and more extreme, it starts to decay in performance. Quite understandable, as it's only seeing the distorted information and is asked to generalize to the more uniform targets. Interestingly, also the DAN classifier seems to struggle here too. While it's performing well at first, it seems that when the skew gets very extreme, it probably relies too much on the source information that it has available to it, and then it also starts to decay in performance.
Can you repeat the difference between SLT and SLS?
SLS here is the source only, so it's only seeing the source information, while SLT is the oracle, has seen only target. So we would expect SLT here to be quite good, which it is, because it's only seen the other sort of classes that we're looking at here. And our model seems to be working quite nicely here in green, very stable, seems to be even outperforming the target oracle at times. And why this is that we're essentially, so we're doing it in 2 steps. We're first finding the portion of the image, and then we're essentially extracting that and pushing that smaller image into the next part. So we're essentially doing an implicit dimensionality reduction with the model itself. So it's not so surprising that it's better.
So you have numbers on the two different parts. How well does it perform with the sort of the extraction, bounding box extraction?
It performs very well. It gets almost perfect extraction very quickly.
It sounds like a simple task.
It sounds like a simple task. But apparently it's not simple to have to go in one go, but it's like the 2 sort of subtasks are easier.
Yeah.
So that's sort of the point. Not so surprising essentially that it's good, but this is something that we construct that fulfills our assumptions, and it should be good. So to go on from that, we try to produce an end-to-end model instead, use this 2-step method, because of course it's more practical just have one classifier that you train with all your data, and then you don't have to think about how to compose these 2 subsequent classifiers. So we adapt Foster RCNN, which is a kind of object detection and labeling network, for doing this by enabling the model to train with these XW and XY tuples that we do have, which is just some small modifications of the losses that are already in the network architecture to begin with. And this network predicts both bounding boxes and labels. So we get sort of a twofer here. We get both the label and actual bounding box information. We argue that it's more practical with an end-to-end method in general, because don't have to think about it. Nicely also with this is that in this architecture, we get object proposals, which is several bounding boxes for each image, of course, and it pulls down to the most likely ones. So we will be able to apply this to multi-label image classification too. So the first experiment using this is based on MS COCO. We have images such as these from indoor and outdoor, where we going to again use bounding box information around these entities. So here it would be around the dog and maybe around the cat and maybe the person and the TV even. So now we're looking at multi-label classification, not multi-class. Source and target are now indoor and outdoor images. How we get these, that we filter for indoor and appliance to get the source, and for outdoor and vehicle for the target. Of course, we remove things like grayscale images and images that seem to fit in both domains. So that might be maybe an indoor image which has a toy car in it, which would maybe map to vehicle. So that would be removed as well. And from this, we seek to classify the labels person, cat, dog, and bird, and see whether these entities occur or not in the image. So the results from this is that we see that we perform quite well. Also here, this is also quite reasonable for our model, since we're still fairly confident that sufficiency is still fulfilled here. Because if we have a box around an entity, it should be enough to, if we can extract all the pixels within that box, to be able to say what the entity is. We also compare with simply using privileged information, but only from the source domain with DALUPI, but that seems to perform about as well as SLS, which is the source-only model. Dan and MDD both seem to not learn very much at all. Unfortunately, it's difficult to say exactly why that is, because it doesn't seem like a very test they would be hard-pressed to find a good answer to, but maybe it's the domains are either too similar or too dissimilar, and it just throws away too much information, perhaps.
I have a question.
Yes.
Perhaps I missed something, but the target, what is the target in the GoPro example?
So the target is, we have images that are coming from indoor and outdoor. So this is the domains. The domains is indoor versus outdoor.
And the target is a classification of these?
Yes. So
what is the class?
The classes are which entities are in each image here. So
and those are several?
Yes.
So
it's multi-label. So
okay.
There are cats, dogs, persons, and birds are the four classes that we're looking for, and we're doing this for indoor versus outdoor then as source and target. Yes. So overall, it seems, again, in this this kind of experiment, it seems that we're doing well with this, even with the end-to-end method that doesn't exactly conform to the theoretical construction which we made. So that's nice to see. We also tried on X-ray classification experiments. So we take from two different X-ray data sets, CheckSpert and the NIH X-ray data sets, source and target. And then we, again, extract bounding boxes as privileged information. There exists already sort of these masks around the problem areas or areas of interest. So we just take the outer bounds of those and produce the boxes that way. One might also use the mask directly, but that we did not do.
So the data set is sort of targeted for segmentation.
Yes, I guess there are segmentations that have been made, and it's been used for that too. But of course, at the test time, we only have the input images, of course. So we apply it again, and in this case, it's a bit more nuanced picture that we see. So now suddenly we do not just handily beat the target oracle. We're the same as the source on atelectasis pathology. On the pleural effusion of pathology, we're again similar to the source, but we're beating the UDA baselines, but we're not beating the target. But in cardiomegaly in the middle, we see that we're pretty far away from the pack, with about 10 points more in test AUC than the rest. So one might wonder why that would be. Probably the cardiomegaly case is most interesting, because we are essentially considering these bounding boxes around a X-ray image. And maybe it's not so clear, maybe if a random piece of a lung is a collapsed lung or with fluid around the lung, which is what alloalexis and pleural effusion is. But cardiomegaly is an enlarged heart. So if you see a heart in the actual bounding box, maybe that's very predictive of that's the issue. So that might be a case. It might also be the case that there's some sort of spurious correlation going on here, or a very simple thing that maybe if you have a bounding box that's close to the center of the image, that's actually predictable of it being a heart, and therefore it would be a cardiomegaly labeling. So that's sort of the issues that we run into here. So again, going back to the assumptions that we have here, it's also a little bit unclear whether it is sufficient with a bounding box in this case, because give a physician these subsets of X-ray images, would they be able to make that labeling correctly? We don't know. We're not physicians. So it sort of speaks to the need for some actual domain expertise in some of these instances, because it's not particularly clear whether sufficiency holds here or not. But still, we do still at least not feel spectacular in anything like that. And also, in this case, we looked at cardiomegaly and added extra X and Y samples to the all methods. And we see here that after a while, the target oracle actually overtakes our method. And as we add more and more, it maintains that lead. And we also see that as we add more and more, even the source only classifier starts to make its way up to be comparable to us. But still, we find that we have quite a large head start because of what we believe to be the sample efficiency of this method.
Or the extra samples without the privileged information.
Yes. So we've seen all the privileged information at start, and then it's just X and Y samples to help the other models catch up. But it still takes quite a few samples before that happens. So to reiterate maybe some of the limitations of this setting is that it may not always be so easy to find a good source of privileged information. Find any source of privileged information may be pretty easy, but it is not entirely clear whether or not that would maybe result in negative transfer or anything else that you don't want in this setting. In the supervised learning case or in the regular DALUPI case, it's more clear that any information that you do give it is good enough. It's going to help you learn faster somehow with sample efficiency. But this might be difficult in this case, because you need to find something that is actually predictable of Y to be able to make use of it efficiently. We still also need to make some sort of judgment about the overlapping support assumption, because we still have it. It just is related to W instead of X. Although, as we argued before, it's probably easier to do in some cases here when W is appropriately chosen. And also, as we talked about with the X-ray example, in some cases, you have to have the domain expert sort of give an opinion about whether a certain privileged information is sufficient or not to make a prediction. So to conclude, this was sort of our idea, the setting DALUPI, which leveraged privileged information for UDA. It builds on these relaxed assumptions where we move the regular assumptions of covariate shift and overlap from X over to these privileged information. But of course, this comes at a cost of collecting these privileged information, so a richer set of variables for training. But our experiments show that it can help reduce errors in your domain transfer and increase your sample efficiency. And yeah, that was all that I had for now. Thank you.
Thank you for this talk. And while everybody in the audience think of one question each, I will start with some questions. So in sort of the experiments where you have the segmentation or the bounding box, and in one step you look at phosphor-RCN, is there a reason for that choice of model, or could you have used some sort of single step model? I mean, single step in another sense here. YOLO is sort of the one pass solution for bounding box prediction.
I wouldn't say that there's a specific reason why we chose faster RCN, more than it's something that did produce and worked with both input images and bounding box data in that sense, and had already all the sort of structure in there. So it felt like a natural choice to modify that and go with that. But I guess going with the EOLA would be a reasonable choice as well.
Can you train these models without the privileged information?
I mean,
you don't have a bounding box, you just have the source and the target.
I guess the end-to-end model would still be trainable, but then that wouldn't be different from your sort of source-only model or target-only model, so to speak.
Yeah.
But the two-step model, that would be an issue because you can do the two steps.
Yeah.
In that case.
But do you mean that you can do this with faster RCN?
I suppose that you would be able to just put in a lot of X and Y tuples and just train using that.
Yeah.
But then it would just be you're using an
arbitrary box.
Yeah, but you're using a large architecture for something that it's not designed to do, being a classifier network. So I don't expect that would do very well.
Yeah, I'm just imagining a case where you have some privileged information. You have the W for some of the pictures, but not all of them.
Yeah, but that's what we're doing in our experiment. We're using every available sort of data point in that way. So if we're losing some that don't have the W, we just put in the X and Y.
Yeah.
And we have the W, we don't have the Y, we put in those instead. So that's sort of the modification that we do, because that's not in the original architecture.
Yeah. Cool. So now you've all had some time to think of questions. So let's hear the questions from the audience. Ida, I think. Yes, but perhaps.
Yeah, hopefully you can hear me. So I was just...
Okay, so perhaps we need to have some sound.
Sorry.
That's better if we have it on the computer.
Can you hear me now?
I don't know.
We cannot hear you, Jesper.
I can hear you very well.
Okay, now maybe?
Okay, can you hear me now?
No.
Otherwise, let's switch to my computer.
I'm sorry.
We'll also switch.
The sound, the microphone here. Jesper?
Yeah.
Now we hear you. Yeah.
Yeah. So I think you kind of alluded to it earlier, but did you observe any, or can you say something in terms of, let's say, the quality of the privileged information? Because I guess there is bound to be some noise in terms of that. So, and I guess if the noise is too high, then you will tend to instead learn only spurious information.
I suppose that's true.
Learn the incorrect stuff, so to speak.
Yeah, I did before. I have started to do some sort of small experimentation with this. But if you think in the first case with the two-step model, of course, if your privileged information is very, very bad and very noisy, you're probably going to get a very poor classifier there. So whenever you're going to go and actually apply that, that's not going to help you very much. But in the end-to-end case, of course, it's going to sort of trip you up. But I don't know how bad it would be. I mean, maybe you could recover if the rest of the information is sufficiently good somehow.
Okay. All right. Thank you.
Thank you.
Do we have some more questions? We get some thank yous in the chat here.
Yeah. Thank you as well.
Otherwise, thank you very much, Adam, for this talk. Very exciting stuff. Next week, welcome back, the September 14th. We will have a visitor from Carnegie Mellon University, Virginia Smith, who's a professor there in the machine learning department. She's working on the evaluation of large-scale learning systems and some relationships to large language models and distributed learning. So welcome back next week.